start. We'll see how it goes.
I've just walked out. Okay, are you ready? We're starting streaming now. Are you sure you want to do that? Yes, okay.
Alright, so hopefully the stream has started and you're hearing me speak. I might just delay a short while to make sure it catches up. So this is, as it says here, going to be the live stream for Term 1 2019. This is for MATH1031, and we're going to try and work over the entire 2018 Session 1 exam, and hopefully we'll get the time for that. Now, I'm being joined by is it Associate Professor, right?
Hi, Liz.
Yes, Associate Professor Adelle Costa.
Okay, hello everyone.
And yeah, so the first thing in the exam is we just want to give you a little bit of a writing guide. So this is very similar to the advice you got in your assignment. So we would like to try you to take any of the lessons you learned from doing the assignment and try and carry that into the exam. So you should be writing full sentences. Sentences should be finishing with full stops. You should aim to have a level of explanation sufficient for someone who didn't know how to solve the problem, but do assume that they are a student like yourself in MATH1031. Don't go too basic. Make sure that your conclusions are written out clearly and give the requested answer. And try to make the explanations concise and clear, but so don't go into unnecessary or irrelevant detail. So I think Adelle's going to start with the first problem. So
yep, absolutely. So thank you, Joshua. And we are going to start from the top and have a look at question 1 from the 2018 paper, which Joshua is just putting up a...
I think I missed one.
That's question 2. We need question 1.
Technical difficulties already.
Oh dear. Never mind. It's okay. We'll do the soft shoe shuffle in the meantime. So our first question is really about matrices and matrix manipulations. Now, some of these have little tricks, and really the question here is for you to be able to demonstrate your ability in matrix manipulation, knowing that things are non-commutative in matrix multiplication, knowing what the identity is, knowing what the inverse is, and how to manipulate these problems. So here we've got a 2 by 2 matrix. Okay, so X is 2 by 2. And we have some information. Okay, it has another thing that x squared is equal to 6x plus the identity I. And of course the identity in this case is going to be a 2 by 2 in order for that matrix addition to be able to be done. Okay, so then we want to have a look at x cubed, because if we look at the question, we are trying to find something that represents x cubed as something, some number times x plus some number times the identity. So what is x cubed? X cubed is of course x times x squared. And we know what x squared is. It's 6x plus I. So, by definition, let's multiply this in. 6 is a scalar, so this becomes 6x squared plus xi. All right, now xi, anything times the identity matrix, is of course the thing itself. So we're going to do two things in this next line. 6, and we instead of x squared, we're actually going to use that definition 6x plus I. And of course, xi just becomes x. So now we can just multiply out. Scalar multiplication, 36x plus 6i plus x. So that's all together, grouping things up, 37x plus 6i. Now remember, what we wanted to do was actually write x cubed is equal to alpha times x plus beta times I. So we can just directly identify alpha is 37 in this case, and beta is equal to 6. All right, so far so good. Now, you can always check your answer, of course. You can multiply each of these things out. What you can do is actually check that that's true and check that this is true with your alpha and beta and actually plug things back in and make sure things are happening. It's actually probably better to wait for your checking until we've done the second half of this question. So the next bit in part B has a very important word, and that word is hence. Okay? Hence means use this information that you've just got to go and do the next bit. Okay? Not or otherwise. If it's or otherwise, it would say hence or otherwise. Or it just might say find or do. But hence, if it's there, it means you must use that information. All right, so let's take this stuff off and move on. All right. Okay, so hence find a solution to x cubed is equal to this 4 by 4, 36 minus 1, 2, 35, x plus another 2 by 2, because they have to be in order to add, 9, 8, 2, 10. Okay, so what we're going to do is use the part from part A and replace x cubed by 37x plus 6i. And of course it's the right hand side is the same. 36, 2 minus 1, 35, x plus 9, 8, 2, 10. And really, in matrix problems, it's writing the matrices out that is the longest operation. Do be careful that you don't miswrite things. I often have that issue. Okay, so here we're still trying to find x. Okay, so we've got x here and an x here. So what we can do is actually factorise this and put 37x minus 36, 2 minus 1, 35, x, taking all the x's over to the left-hand side and moving this 6i over to the right-hand side, 9, 8, 2, 10, minus 6i. Now we can factorise that left-hand side by remembering that we can actually write this as 37ix. So here we can have 37i, which is 37, 0, 0, 37. Remember, I has ones walking down the leading diagonal and zeros elsewhere. But we're multiplying that throughout by 37, minus our second matrix, coefficient matrix, x. And, of course, here we're going to have 9, 8, 2, 10, minus 6, 1, 0, 0, 1. And of course, we can not fall over and simplify this down. 9 minus 6 is 3, 8 minus 0 is 8, 2 minus 0 is 2, 10 minus 6 is 4. Okay. And on our left-hand side, we've got 1, 1, minus 2, 2, x is equal to this, 3, 8, 2, 4. Okay, so if this here on the right-hand side was actually a 2-row, 1-column, 2 by 1 matrix, then we could use an augmented system to find x. But here we've got 2 columns. So what we're going to do is actually recognise that x is a 2 by 2 matrix and write out what the left-hand side would look like for each one of the elements. All right, let's make some space. All right, so just to reiterate, we had 1, 1, minus 2, 2 times our x, which we'll call A, B, C and D. Okay, and that right-hand side was 3, 8, 2 and 4. Okay, where we have let x be A, B, C and D. Okay, so let's look at each element in turn. So let's start by equating the values at each position, row and column. So if we go row and column, and the value for 1, 1, that's this position here, we have 1 times A plus 1 times C. A plus C is equal to 3. Okay? For the second row, first column, that's this one, we've got second row minus 2 times A plus 2 times C is equal to 2. For the first row, second column, that we have first row with the second column, that's 1 times B plus D is equal to 8. And for the second row, second column, what we have is minus 2B plus 2D is equal to 4. So now we have 4 unknowns, A, B, C and D, and 4 equations. So hopefully we will have a unique solution. So we could use simultaneous equations, but why not use an augmented matrix for our unknowns A, B, C and D, and use our matrix methods, reduced to row echelon form to solve for this. So let's create an augmented matrix. Okay, so the order is A, B, C and D. Okay, so our first equation says 1 times A plus 0 times B plus 1 times C plus 0 times D is equal to 3. The second equation says minus 2A plus 0B plus 2C plus 0D is 2. Our third equation says 0A plus 1B plus 0C plus 1D is equal to 8. And our fourth equation says 0A minus 2B plus 0C plus 2D is equal to 4. Okay, so now let's use our knowledge about matrix manipulations to reduce this to row echelon form. First of all, remember, identify where your pivots are. They're the first non-zero entries in the matrix, in each row. So, this one is fine, it's great. But this one we do not want to be there. We would like to get rid of this one and then clean out below each pivot. Remember, your augmented form becomes in row echelon form when the pivots go down and to the right. Okay, so I would like to get rid of this minus 2. And to be honest, I'm going to get rid of this one as well using this row. So, firstly, what I'm going to do is take row 2 and I'm going to add 2 lots of row 1. And this is going to give me row 1 stays the same. Row 2 becomes row 2 plus 2 copies of row 1. That's 0, 0 plus 2 copies of 0, 2 plus 2 copies of 1, that's 4. And 0 plus 2 copies of 0 is 0. 2 plus 2 times 3, that's going to give me 8. Oh, excuse me. And now I'm going to leave this one here alone because I can see already I have one pivot here and one pivot here, but no pivot in that second column. So I'm going to leave row 3 alone, and it's going to have 0, 1, 0, 1, 8. And then for row 4, I'm going to have row 4, and I am going to add 2 copies of row 3. And in that way, this minus 2 is going to become 0. So 0 plus 2 times 0 is 0. Minus 2 plus 2 times 1 is 0. 0 plus 2 times 0 is 0. 2 plus 2 times 1 is 4. 4 plus 2 times 8, that's 20. And we can identify our other pivots here and here. Now, every column has a pivot, but we're not going down and to the right. So I'm just going to swap the rows around, and I'm going to swap row 2 and row 3. And that will give me my matrix in row echelon form. And 0, 1, 0, 1, 8, 0, 0, 4, 0, 8, and 0, 0, 0, 4, 20. Okay, here's the pivots going down and to the right. Okay, remember these are also known as leading rows, leading columns where the pivots are. Okay, so it's in row echelon form. We can now back substitute. And look, every single column has a pivot and there's no contradiction. We can certainly solve this, so it's definitely got a unique solution. All right, so back substitution. All right, remember it's A, B, C, and D. So row 4 says that 4D is equal to 20. In other words, D is equal to 5. All right. Row 3 says 4C is equal to 8. So C is equal to 2. All right, I'm going to make some room. Okay, row 2. Row 2 says that B plus D is equal to 8. Okay, so B is equal to 8 minus D, which is 8 minus 5, so that's 3. And row 1 says that A plus C is equal to 3. So A is 3 minus C, that's 3 minus 2, that's 1. So here our X is A, 1, B, 3, C, 2, and D, 5. All right, so we can check. And I won't do this here, I'll leave this for you, but you want to check x squared. All right, multiply this x by itself. See what you get. And you want to check that it's equal to 6x plus I. All right, so substitute this x both into the left-hand side and the right-hand side and make sure that they become the same thing. You can also then check that x cubed is actually equal to our 37x plus 6i. So by substituting this value in, you can make sure that you haven't made some stupid numerical slip. All right, so that's part 1 of the problem. And shall we move on, Josh? Or are there any questions from the stream that we should have a look at?
No, the stream's been very quiet.
Oh, well, never mind. Hopefully you're all following along well.
Yeah, so I will say, just to sort of break up the stream, yeah, I think checking is a good idea. Maybe you want to move on and do another problem and then come back and check if you're,
yes, that's a good point.
It's not that, one thing, you also want to get time to work on the other problems, but I think it's also, you'll be doing all these calculations, your mind's in a certain space where you'll be much better at spotting your own mistakes if you come back sort of a little bit later.
Yes, do a first draft of everything and then come back and check. It's a good idea to always check, however.
Yeah, and right. Now I did have one question about this. I could spot a different way of solving this,
yeah.
which I'm sure you also thought of. Although I do like this method because this is very fail-safe. This will always work. But one thing you might notice is actually this 2x2 matrix here is actually an invertible matrix.
Yes.
So a very clever person might think to just pre-multiply by the inverse and save themselves a lot of calculation. That being said, I guess you could have a non-invertible matrix here, and then you still have equations to solve.
Yes.
Still have
This one will always work.
Yes.
Joshua is absolutely right. If this is invertible, then multiplying both the left and right-hand side by the inverse gets you the matrix directly.
Yes.
So have a think about which way suits you best, but both will work.
Yeah.
In some ways I did it this way actually also to give you a run through on augmented matrices as well.
Yes. I mean, I think I have seen certain problems where this was not invertible, but then people just gave up, not realizing they have other tools. So if it's not invertible, you still have other tools to solve these equations. So don't just get focused on the inverse.
Yes, and this method will also work if it's not 2x2.
Yes.
All right, so let's clean the board and go on to question 2. All right, so let's look at the question. It says, a fisheries laboratory needs to prepare 300 litres of salt solution to replenish their tropical tank with salt solution of concentration 10 grams per litre. They have a supply of fresh water, a supply of local seawater at 6 grams per litre and a supply of concentrated salt solution at 36 grams per litre. Let X, Y and Z be the quantity in litres of the fresh water, seawater and concentrated solution used to make the mixture. Okay, so we need to extract information, but what are we trying to do? We want to set up 2 linear equations for finding the values of X, Y and Z. And in part B, noticing that the variables must be greater than or equal to 0, they are actually quantities after all of a liquid, describe the range of feasible values of X, Y and Z, and then how much of each type of water should be used to make the mixture if they want to use as much of the local seawater as possible. Okay, so let's start by extracting the information. All right, so X is the litres, or the volume of fresh water. In other words, that's no salt, right? Y is the litres of 6 grams per litre seawater. And Z is the litres of 36 grams per litre and that's salt water. Okay, so what is it that we want? We want 300 litres of 10 grams per litre solution. Okay, so first of all, let's just recap what's the actual principle we're talking about here. So concentration is equal to the grams, in this case, of salt over the litres of water. Okay, so that's the physical principle we're using. All right, so concentration is the amount of the substance divided by the volume that it's dispersed in. Okay, so what are the two things we know that we want? We want a particular volume and we want a particular concentration. So actually, what we can break it down into is I want a particular volume and thus I need a certain amount of salt in total that's in that volume. Okay, so the volume we want, well, that's 300 litres. How do we get 300 litres? Well, we have 3 solutions that we're plonking in the one bucket and we want it to be 300 litres. So that tells me that the amount, the litres of fresh water and the litres of seawater and the litres of the salt water all add up to 300 litres. So X plus Y plus Z is equal to 300. All right, so that's the volume. That's the concentration is the amount of salt in total divided by the volume. So how much salt do we want? The total salt. The total salt is going to be equal to 10 grams for every litre of solution. So the total salt is 10 grams times 300 litres. In other words, 3,000 grams. How do we get it? Well, we use that same idea that the grams of salt is the litres of the solution times the concentration of the solution and add all of our components up. So that, just to write that out, is concentration, or rather, concentration times volume. Just rewriting it. So how much salt do we have in the fresh water? The concentration of salt in fresh water is 0, and we've got X litres of it. We've got then Y litres of 6 grams per litre seawater, so that's 6 grams every litre times Y litres of seawater, plus then 36 grams for every litre of salt water, and we've got Z litres of salt water. So that is going to be our 10 grams per litre that we want for our 300 litres. And so here we have 2 equations for 3 unknowns. Okay, this is our first equation, and this is our second equation, which you can pretty up and take away the brackets if you'd like. You can even take away the whole first term here because it's 0 times x. Okay, so these are our 2 equations. So I've got 36 written down. Is it 35? Yes, 36. Ah, all right. My notes have a 35 instead of a 36, but I'm going to get it right, I'm sure. Okay, so if we have 3 unknowns and 2 equations, we don't have sufficient information to solve this uniquely, okay? Because at minimum you would need 3 pieces of information for 3 unknowns to solve it uniquely. All right, so let's try and solve this system. I'm going to rub off the top. And whilst these are still there, I am going to write these 2 equations as an augmented matrix for x, y and z. So 1x plus 1y plus 1z is equal to 300. That's the volume equation. 0x plus 6y plus 36z is equal to 3000. Okay, now, is this augmented matrix in row echelon form? Here's the first pivot and here's the second pivot. Yes, it's in row echelon form. The pivots go down and to the right. So we can go straight to back substitution now. So let me just take that off. Okay, so oops, can't spell. All right, so row 2 says, and remember it's x, y and z, it says 6y plus 36z is equal to 3000. Okay, but column 3 has no pivot. So z is a parameter of the solution. Z just equals z. You can call it t, but let's just call it z. Okay, so 6y is equal to 3000 minus 36z. Or in other words, y is equal to 500 minus 6z. All right, let's flow this back up, back substituting up to row 1. Row 1 says x plus y plus z is equal to 300. In other words, x is equal to 300 minus y minus z. That's equal to 300 minus 500 minus 6z. Note the brackets, it's important, the minus sign applies to both bits. And then minus z. So this is going to be equal to 300 minus 500, that's minus 200. And then we've got minus minus, that's plus 6z minus z, plus 5z. All right, so we actually have now a solution in terms of our parameter z. So x, y, z is equal to, well, x is minus 200 plus 5z. Y is 500 minus 6z, and z is just z. Okay, so all of these have to be positive quantities, or rather non-negative. They can be 0. So x, y and z are non-negative. Okay, So first of all, that means that z is greater than or equal to 0. But that's not terribly useful. What we can do and tie the ranges down more is by looking at x and y. So for x being greater than or equal to 0, minus 200 plus 5z is greater than or equal to 0. So 5z is greater than or equal to 200. Z, thus, has to be greater than or equal to 40. All right, so what about for y greater than or equal to 0? That says that 500 minus 6z is greater than or equal to 0. So 500 is greater than or equal to 6z. Okay, so this is not going to be as pretty. We're going to have 250 over 3 is greater than or equal to z. Okay, 500 on 6, 250 on 3. Okay, so now we've got a range of values for z. So z is between 40 and 250 on 3, putting these things together. All right, we actually have to look at the range, of course, of x and y as well, because that's going to be dependent on this z. So x determines that z has to be greater than or equal to 40. When z equals 40, putting z equals 40 in here gives us x equals 0. But if it's bigger than 40, then it could range upwards. This is the upper bound that we've got for z. So if z is equal to 250 on 3, that tells us that x is equal to minus 200 plus 5 times 250 on 3. And that gives us the upper bound for x. If z equals 40, remember, x is equal to 0. Similarly, if we look at y, when z is 250 on 3, we end up with y equals 0. But when z goes to 40, the lower bound, we're taking away as little as possible here in y. So if z is equal to 40, that tells us that y is equal to 500 minus 6z, and that's 500 minus 6 times 40. And 6 times 40, well, that's going to be 240. So that's going to be 260. Okay, so we now have y ranging between 0 and 260, and x ranging between 0 and this, which I haven't actually calculated. And z, of course, is already between here, and that's guaranteeing, of course, that it's non-negative. All right, so that tells us the values of the range of feasible values for x, y, and z. In your working, I don't have a calculator on me, and you will, you should calculate this value so that you can actually write it down. All right, so no. Joshua is offering me a calculator, but I'm going to continue on because actually what's more important is to know what the concepts are. Okay, so here you've got to demonstrate that you understand that you have a parameter in this solution and that the parameter can change value, and that will change all three values for x, y, and z in lockstep. So it's a triplet of values. There's an infinite number of triplets, but they are very much locked together. So you're representing this as a particular set of infinite solutions. So now we'd like to collapse that down to a very particular solution. We would like to know how much of each type of water should be used to make the mixture they want, the 300 litres of 10 grams per litre solution, yeah, and they want to use as much local seawater as possible. Now, local seawater is the y variable. So I would like to maximise y. Okay, so here is y, all right, it's that second row. In order to make this number as big as possible, I'd really like to make z as small as possible because I'm taking stuff away. And of course z is non-negative. Now, if you look here, and this is why I'm not particularly concerned about the upper bound of z, z is as small as possible when z is 40. That's the lower end of its range. So if z is 40, y is going to be as big as possible. Okay, so I'm just going to write the range. So 40 is less than or equal to z is less than or equal to, here we go, minus 200 plus 5 times 250 on 3. All right, I'm going to make some more room. Okay, to use as much seawater, which is the y, as possible, we want y equals 500 minus 6z to be as large as possible, i.e. make z as small as possible. Z is going to be on that lower end, 40. Okay, so i.e. y is going to be 500 minus 6 times 40, just the 240, so that's 260. And remember, it's litres, all right? What about x? What about z? Well, x is minus 200 plus 5z. Well, 5 times 40, that's 200, that's 0 litres. Oops. And, of course, z is just 40. So, to the solution to the solution is 0 litres of fresh water. That's x. 260 litres of seawater. That's y. And z, that's 40 litres of salt solution. Do a quick check. Add them up. Do we have 300 litres? Yes. So this is a great quick check that you can do. So here we have set up the equations to extract the information from the words. We've worked out the rule that's connecting the information together. In this case, we have concentration is the amount of the salt divided by the volume. And then we've put that information into two equations relating the different amounts of the three different solutions. We've solved those two equations to get a infinite set of solutions for x, y and z, linked together by the parameter z. And we've then said, okay, each one of those, x, y and z, has to be non-negative. And so we've restricted the range. In the third part, we wanted to make y as big as possible, and because it had an expression which had z as a negative factor in it, we wanted to make z as small as possible. And that then allowed us to get this particular solution to our problem. All right, are there any questions, Joshua, from anyone?
The chat's still very quiet.
Okay, that's fine, as long as everyone's enjoying themselves.
I was remembering something the director of first year did say before we came to the live stream to me. He did want me to remind students about what the passing grade for the exam was. Do you know what the passing grade would be for the exam? Well, actually, the passing grade for the exam, so the mark you need to know that you're passing is 0. Because actually students...
yes, of course.
Yeah, so don't feel that... I mean, if you go to the exam and you do find it's quite hard, well, congratulations, you've passed the course because you've sat the exam. I mean, actually, you don't even need to come to the exam. But yeah, don't worry so much. These questions, they're supposed to be a bit harder than the stuff you saw during the session and the stuff you're doing in the mastery test. So even if you feel like, oh, this was a really hard exam, I didn't do very well, you've still passed.
That's absolutely right. Anything here is just cream. So the idea is that you've already passed the course. Of course, to pass the exam, that's a different matter, but you've already passed the course. All right, so shall we continue to the next question? All right, so we have a question here that has two interrelated quantities. And it says that the quantities are very boringly called x and y, and they're measured in the laboratory. And we're given a table of the values, x and y. So x is just setting 1, 2, 3, 4. This is usually called our independent variable, and then y is then measured when x is a particular value, and it's its dependent variable, and you can see that it's increasing. Okay, the numbers are going up. But they've also given us a table of values where they've taken the logarithm of both the x and the y. All right, so this also has a relationship between a capital X variable, which is our log of little x, and a capital Y, which is the log of little y. Now, the first question that we're going to be asked is about what the relationship might be between those variables. And what we can see is that they've plotted 3 different types of, I'm going to rub this out while I talk, 3 different graphs. Okay, so what you need to do is have a look at the graphs. Now, we would like to know what the relationship is. Now, straight lines are really easy to visualize, okay? Whereas a curve, well, you can see if a set of points goes around a curve, but you can't really tell exactly what curve it is. Could it be a quadratic? Could it be an exponential? Could it just be some other relationship? You don't know. But when it's a straight line, your eye is very good at picking up that these lines basically are collinear. They're lying along a straight line. So have a look at those 3 plots. You can see that you've got the first one on the left is just our little y times by little x. Okay, and you can see that it's certainly an increasing function. Those dots go up as they go to the right, but it certainly looks like the amount that they go up as they step to the right increases. So this does not look like a straight line. On the other hand, the second plot, capital Y, which is our log of y against x, does certainly look like a straight line. It even goes through the origin. Very close. So it's a real candidate. The third one, capital Y against capital X, well, it looks a bit like a straight line, but if you make sure that you can see, and I'm going to try and wave my hand if I can. I don't know if I can. There we go. Write down, and I'm trying to do the weather map idea. So the idea is, if you look at the origin, right on that last plot, I'm going to try it a little bit more. So down here, then you are going to see that that point is not collinear. It doesn't lie on a line with the other points. So what we're going to do is say, I think that the best looking line out of those three belongs to capital Y against X. Okay? So the trend that looks most linear is Y, capital Y, against X. Okay? So that tells us the quantities are related by capital Y is equal to some mx plus b, because that's the equation of a straight line. Okay? But it's the capital Y that is the straight line y coordinate, and x, little x, is the x coordinate, the horizontal coordinate. So what we'd like to actually know, though, is what's the relationship between little x and little y. So to understand that, we need to know that capital Y is actually log of y, little y. So log y is mx plus b. I'd like to make y the subject, so I'd like it y equals something. So I need to take away the logarithm here. I do that by taking the exponential throughout. So e to the log y, I'm being verbose, is equal to e to the whole right-hand side, mx plus b. Because the exponential and the logarithm are inverse functions, this just becomes y is equal to e to the mx, and using my power rules, e to the b. Because if I've got an addition in my exponent, it's e to the first bit times e to the second bit. All right, now e to the b. Well, b is just a number, so e to the b is also just a number. And so I can write this as a e to the mx, where a is equal to e to the b. All right, and so our relationship is y is equal to e to the mx, and we have just a constant at the front, but we know how that relates to a line, which we can then create a line of best fit to determine m and b, and thus our exponent m here, and a, our coefficient. Because once we know b, we can work out what a is. All right. So now our next part, in part B, we would like to find the values of a and m for the equation that we have chosen. So I have to say, it's actually quite important that you've chosen the right equation at this point. It doesn't mean you can't do the fit, but the fit that you will have will not necessarily best represent that trend that we saw. Okay, so let's take this off. All right, so.
Should we show them the maple output just so they can see it?
What we're going to need to do first is to talk about the least squares line of best fit. And then we're going to have a look at the maple output. Because if we want to fit, we want to fit this expression, capital Y, is equal to mx plus b with the data. So actually, I do need the data up, right? Because how do we do this? What we're going to do is assume that each one of those points actually satisfies the equation. Okay? So if we want to fit this, then what we're going to do is substitute each of the pairs of data, x and capital Y, into y equals mx plus b. Now, I'm going to actually rewrite this in the other way round with the equal sign and the things the other slight different way, because I'm going to write this as x times m plus b equals y. Okay? And then I need to make sure I use the x values from that first table, so 1, 2, 3, 4, 5, 6, but then the capital Y values from that bottom table. All right, so let's do the pairs. We're going to have 1 for x, m plus b, is equal to capital Y when little x equals 1, that's 3.22. Then 2m plus b is equal to 4.73. 3m plus b is equal to 6.22. 4m plus b is equal to 7.72. 5m plus b is equal to 9.22. And 6m plus b is equal to 10.7. All right, so this is as if those points satisfy the equation. So we can write this as a matrix equation. So let's write that over here, okay? So we're going to have the coefficients of m and b. So 1, 2, 3, 4, 5, 6. 1, 1, 1, 1, 1, 1 times mb is equal to that right hand side, 3.22, 4.73, 6.22, 7.72, 9.22 and 10.7. Notice each one of those numbers on the right hand side is only an approximation. It has 3 significant figures. Okay, so this is the most figures you should ever report. Okay, so now we're going to leave this matrix equation up and we're going to look at the Maple code. Okay, so in the Maple code we've got some really useful information. Okay, so on the left here you can see that that matrix actually corresponds to the matrix A in the Maple code. Okay, so this bit here is the matrix A. All right, M and B are our unknowns. And I can see this matrix in the Maple code in some manipulations, but it's not there explicitly. So let's just call it R. All right, let's call it the right-hand side. Okay, so I'll just make some room for myself. We have a matrix equation A times our MB, unknown, is equal to R, our right-hand side, where A is this matrix on the left, the coefficient matrix, also A in our Maple code, and R is this column matrix of our right-hand side, the log of little y, capital Y. All right, so let's take this matrix equation, and in order to get M and B by themselves, I really would like to just have the inverse of A and multiply both sides by the inverse. But I can't because A is not square. And so I am going to multiply throughout by A transpose on the left. So A transpose times A times our M and B unknown matrix is equal to A to the T R. Okay? So this is 1, 2, 3, 4, 5, 6, 1, 1, 1, 1, 1, 1, and 3.22, 4.73, 6.22, 7.72, 9.22, and 10.7. So this bit here is in the Maple code. If you look, you can see that it's actually the Maple matrix B. Okay? So this bit is equal to B. Interestingly, also, we can see that A transpose times A is also in the Maple code, and it is the matrix M. All right? So we have M times my unknown MB is equal to B. All right? So now we can use that Maple code and the manipulations to our advantage. Okay, so we can use the matrix outputs, okay, because it's given us what M is and it's given us what B is. So we don't actually have to do this multiplication ourselves. All right, so I'm going to just erase and rewrite some of this.
So while Adelle is erasing it, I might just point out, actually you only needed the first half of the Maple code, so don't be distracted by how much code there is. You have to look at it and find exactly what it is you're looking for.
And, you know, it might be because, you know, you may have chosen a different trend. You might not have chosen capital Y versus X. So it's not just going to tell you exactly what the answer is. The Maple code is helpful, but it also has red herrings in it, things that may not be useful. So this you can consider as possibly useful information, not all useful information. It's a good point. Okay, so we have our matrix equation. So it's M times our unknowns, M and B, is equal to capital B, using the letters from the Maple code. Okay, so now M is square. In fact, it's 2 by 2. So I can multiply throughout by the inverse of M on the left-hand side. To be verbose, M inverse M MB is equal to M inverse B. This, of course, is the identity. So MB is equal to M inverse times B. Now we're going to stick in the Maple outputs. Okay? So this is equal to 91, 21, 21, 6 inverse times our B, which is 172.52 and 41.81. All right, according to the Maple output. Now we're on our own, but that's okay. We can now do this inverse because it's a 2 by 2. So we can say this is 1 over 91 times 6 minus 21 times 21. We swap the leading diagonals and we stick minus signs in front of the off diagonals. That's our M inverse. We still have B sticking around ready to be multiplied. Okay, so this is 1 over 105, and we've got 6 minus 21 minus 21, 91, 172.52, 41.81, and matrix multiplying across the row and down the column. 6 times 172.52 minus 21 times 41.81, and so on. You calculate it up and you get approximately 1.496 and 1.731. Note, I've put a few more decimal places than really justified, but I can use those and I can just leave things in that full form because I'm not quite finished yet. Okay, so the fit is y is equal to mx plus b. Okay, corresponding to, to y is equal to ae to the mx, a is equal to e to the b. All right, and the parameters are m is approximately 1.73 and a is e to the b, which is 1.496, which is equal to 5.65. Notice 3 significant figures. Significant figures don't care where the decimal place is. Okay, so this is 1, 2, 3 significant figures, 1, 2, 3 significant figures, just the same as our original information. Don't include more because you've only used 3 significant figures at the start, and any other decimal places or extra figures may be erroneous due to round off error and so on. So this then gives us our line of best fit and thus our exponential of best fit for this particular data set. All right, so
is it sometimes worth trying to see whether it matches the plot? I guess it's hard to see on this one.
it is hard to see. What you can do is stick in a point or two into our exponential and some of the original data and see if the numbers are approximately the same. Remember, they're not going to be identical because this is a best fit and not all of these points actually going through the curve.
Yes, so looking at the plot, which I just brought back up,
Yes.
because the parameters we found, so this a and this m, they're for the exponential.
Mm-hmm.
So I don't think the first number can really be spotted because it's down at 5, but you see it gets very large. So it might be best to try and put in a number like maybe the last one. See what happens when you plug in x equals 6. That should give you a number about the same magnitude as this high point over here.
And you can also check these numbers by putting in the numbers for x and comparing it to that second plot, capital Y versus x. Which is approximately on Joshua's stomach at the moment.
Yeah, that's right. It's hard to position.
The centre one.
Yes,
that's
so
right.
You can see, so, I mean, for example, where is B? So B would be when x is equal to, actually I don't think x equals 0 appears on the plot. It starts at x equals 1.
No, and it shouldn't actually, because if you take the log of 0, what's going to happen? You're going to go to minus infinity. That's why this data set works, because we started with x equals 1.
Right. Okay.
All right, so over to you, Josh.
Yep. Alright, so for image number, yep, there it is. So we're moving on to question 2, and I'll do the entirety of question 2. Adelle can interrupt me when I'm doing things wrong. Let's see. So we're actually talking about 2 functions you may not have seen before, but all the information you need to answer this question is provided in the text. So it's talking about these so-called hyperbolic trig functions. These are related to the regular trig functions you know in some sense. But all we want to do is try and get the... I didn't think that's how you spelled Maclaurin. Okay, we want to get the Maclaurin series for the functions defined by this. And we are told that the derivative of the hyperbolic cos is the hyperbolic sine, and the derivative of the hyperbolic sine is the hyperbolic cos. These are even nicer than the trig functions in that sense. When you were dealing with trig functions, you always had that annoying minus sign popping in. Here you don't have that. So to begin with, well, I'm going to have to talk about this function cosh, the hyperbolic cosine, quite a lot. I might just start by making my life a little easier and introducing some notation. So I'm just going to let r of x equal to this hyperbolic cosine of x. Just because I'm going to be talking about this a lot. One symbol for me is easier to write than 4 symbols if I have to keep referring to it. Now, to get the Maclaurin series, we need to know what the function is doing around 0, so I need to know its derivatives. And it says here I need 3 non-zero terms, so I need at least 3 non-zero derivatives. So let's just see what the information here tells us about the derivative of this hyperbolic cos. So we can calculate. Well, let's try and get the first derivative of the hyperbolic cos. So by definition, this is just the derivative of cosh, sometimes called cosh. And it actually tells me right here that the derivative of hyperbolic cos is hyperbolic sine. So now if I want the second derivative, well, that's just going to be the derivative of the first derivative, which we know is the hyperbolic sine. And according to the information here, the hyperbolic sine's derivative is just hyperbolic cos. And we can continue. So I can see I'm going to need a few more. So I will do 1 or 2 more. So derivative of hyperbolic cos, that was just hyperbolic sine, and I could just say there is a definite pattern following here. I'll do 1 more just for completeness. The derivative of the fourth derivative of this function r is going to be the derivative of sine, hyperbolic sine, which is just the hyperbolic cos. And that pattern just continues. So that's nice, because now I can work out what these derivatives are at 0 using the other information we're provided with. So at x equals 0, the first thing we're told, I want to know what is the function value of this at 0. Well, it is just the hyperbolic cosine at 0, and much like the regular cosine, at 0 this starts at 1. We can continue to get the first derivative. So the first derivative is going to be the hyperbolic sine at 0, and just like the regular sine, it actually starts with at value 0. And of course, this pattern will just continue. So I can see, if I'm going to look at the expansion, I only have 1 non-zero term so far. I'll need to get a few more. So second derivative is nice. It is just the cosine, the hyperbolic sine at 0, which is 1. The third derivative at 0 is just sine of 0, which is 0. And finally, the fourth derivative at 0 is just the hyperbolic cos of 0, which is 1. And you could see that this pattern does continue. So this is good, because now when I'm going to take my Maclaurin series formula, well, this will give me a non-zero term, this will give me a non-zero term, and so will this last one. So I'll get 3 non-zero terms in my Maclaurin series. Alright, so I need a little bit of space. So the Maclaurin series for, well, r of x, which is the same as the hyperbolic cos of x, is, that's given by, you start with the initial value, so you start with the value at 0, you then have a linear term based on the first derivative, a quadratic term which comes from the second derivative and has this little correction factor of 2 factorial, or this little factor of 2 factorial. You'll have a third derivative evaluated at 0 times the cubic and over a 3 factorial. And we do need one more term, so the fourth derivative at 0. And that's all divided by 4 factorial. And really there are more terms. So looking at what we have, so here we have it starts at 1, then a 0, then a 1, then a 0, then a 1. So we're going to get constant term of 0. There'll be no linear term. I'm still going to write this out just to make it visible. There'll be a 1 over 2 factorial. Now 2 factorial is just 2 times 1, so it's a half x squared. There is not going to be a cubic term, so it's 0 times the cube. And I will have, well, I might leave that 4 factorial the way it's written and write it as x to the 4 factorial. And there are other terms. And I think it's polite to write this slightly neater. Get rid of the terms which are actually not contributing. And you can see actually this is very similar if you remember the Maclaurin series for cosine, but that had alternating minus signs. The hyperbolic cosine is even nicer. You don't see any minus signs.
I might actually say
yeah.
something. And it doesn't have the minus signs because it goes cosh and then shine and cosh and then shine, and there's no minus sign like when you differentiate cos and it goes to minus sign. A nice thing about the Maclaurin series that I might mention is that a Maclaurin series, if you just look at the first few terms, it says let's start at 0 at the height of the function and walk along the tangent line that goes through the curve at that point. And then we know that if we take a step on the tangent, if we go too far, we'll actually deviate from where the actual curve is going. So this is another correction for the curvature of the function at that point. And then another smaller correction for the curvature of the curvature, and the curvature of the curvature of the curvature, and so on and so on and so on. So we're actually turning any function into a polynomial. The first bit is the actual point that you start at when x is 0, and then the tangent line, and then the curve of the tangent line, and so on. And so in this way we can get more and more accuracy, and this is not a bad approximation as long as we don't walk too far away from 0.
Thanks.
All right, and on to the next question.
Yes. And actually that point's going to be very, very relevant for the next question, because for the next question we're actually going to be comparing different Maclaurin series. So we do actually need this, so I might just store that away over here, just a reminder that the hyperbolic cosine, at least the first 3 terms in the series, the Maclaurin series, is 1 plus x squared over 2 plus x to the 4 over 4 factorial and other terms. Now the next part of the question gives us some functions and gives us Maclaurin series for some of these functions, or almost gives us Maclaurin series for these functions. And then we're asked to use this information to work out which of these plots actually correspond, so which of the curves in this plot actually corresponds to those functions. So the first one's quite easy. So let's just write out what the Maclaurin series for these different curves are. So for part B, the Maclaurin series for the given functions are, well, the first one's quite nice. They actually just told us exactly what this Maclaurin series is. So you want to look at the function 1 over 1 plus x, and they say it can be, well, the Maclaurin series for this is just 1 minus x plus x squared, and then there are other higher correction terms, but we're actually not going to need them for this problem. The next one, they don't actually give us the Maclaurin series for this, so we're given g of x is equal to e to the minus x. What we are told is the Maclaurin series just for e to the x, but that really does give us the other one, because this is just e with a minus x inside. So this is just going to be pulling out the series. It's 1 plus a minus x plus a minus x squared over 2. And again, there are going to be higher order corrections, but we only really want to go up to this term, as we'll see. So that is going to be 1 minus x, and well, when you square minus x, you just get x squared. I didn't need a comma there. And the last one, well, it's the hyperbolic cos with an interesting argument inside, and then we're subtracting off x. So this is why we need our part A. So from part A, we get that h of x is equal to, well, it's going to be the hyperbolic cos evaluated at x on 2 minus x. Now we are told that we can write hyperbolic, the Maclaurin series for this is just 1 plus, well, this is an x on 2, so I'm just going to take this x on 2 and put it wherever I see an x here. It's going to be 1 plus x over 2 squared over 2, and there is a fourth order term here, but looking at what they're giving me, I don't really need that. So I'm not going to write it. You can write it down, but I'm not going to need it. And I'm going to subtract off x. So rewritten, so bringing this x into this polynomial gives me 1 minus x plus, well, x over 2 squared is x squared over 4. It can be written as x squared over 8. And there will be higher order terms, but that's all I really want. And what's nice about this is that these functions are very similar for small values of x. They all start with they all start at 1 when x equals 0, and they all have this nice correction term of a minus x, so they're going to have the same slope. What really distinguishes them is this term here. So these, I've written this wrong. There are other terms there. It's really these terms here. These terms are different for all of them. They're saying that I can't tell the functions apart looking at how they start. I can't tell them apart looking at their slope. What I can tell is them apart is looking at their curvature, looking at their second derivative. Alright. So I'm going to just save this. Boards are never quite large enough. So we had f of x was equal to 1 minus x plus x squared and other terms. G of x we found was equal to 1 minus x plus x squared over 2, other terms. And h of x is equal to 1 minus x plus x squared over 8. Now, I really do want the person who's going to read my answer to understand what I'm trying to say, so I am going to write down what I said in words. So all these functions start at 1 when x equals 0, and all these functions have slope minus 1 at x equals 0. So if you're looking at this plot, you can see they all start coming out the same way. I can't really tell the difference between them. But what I can see is that the curvature is different. So what distinguishes them is the second derivative. At x equals 0. Now, just looking at what we have, well, it's a comparison between these three terms. So because, well, you can see that x squared is going to be larger than x squared over 2, and that's going to be larger than x squared over 8. So because we can make this observation, then, well, I'm not sure what happens once we go too far away, but at least close to 0, so close to 0, we have, well, I'm going to have that h of x is going to be smaller than g of x, and that itself is going to be smaller than f of x. So now I can look at this plot and I can see which curve is which. The one on the top has to be f of x. This is the dotted one in the plot. So hence f is the top curve. In this plot it is dotted. G is the middle curve. Which in this plot is a solid line. Solid. And finally, h is going to be this bottom one, the dashed curve. This is a plotted using a dashed curve. Okay. So you do need to get part A right if you want to get this part done. And it really does come down to just observing that the behavior of these functions, it's very similar when you look at the first two terms. It's the third term that's really picking out the behavior. Any comments?
Yes, and you could substitute some points, for instance, and have an actual look at what values these might take. And just looking at these three terms, you could substitute in x equals 1, and you will notice that, of course, you don't end up with those heights, right? If you just substituted 1 into these first three terms, it would be 1 minus 1. All of those first two would go to 0, and then you would have 1, a half, and an eighth, okay? But remember, of course, there are other terms, there's extra terms, some of which are negative, and so you won't see the actual numbers that come out at the height if you look at the plot when x is equal to 1, but the relative position of the three functions is going to be preserved because all of those correction factors are necessarily smaller than the previous one. So each term that you keep adding in the Maclaurin series here gets smaller and smaller and smaller. So just by plugging in, say, x equals 1, you can see that this one is going to be bigger than this one, is going to be bigger than this one. And that was a nice cross-check so that you can see those curves walking down in height. All right. move you on to the next question.
So this next question, it is quite a big one. Now, I might say, this, if you look in the top left corner, it does tell you here what the marks were for this question. There won't be any marks given on the exam when you're sitting it. So you won't be able to, you won't have that thing here which says it's 11 marks. But so I just want to point out that this particular question is worth over half the marks for one of the booklets. So it is quite a big question. So if you're doing this question, if you've done this question and you found it very hard, it's because it is supposed to be quite substantial. There are a lot of parts to this question. So we do have a setup here, and it's good to read what they're talking about. So we do have a population of trout in a pond, and we're told that the trout, so initially they had 100 trout at year 1, but the trout are going to double. They doubled after the first year. So that's information, that's already telling you another data point. It's telling you that after 1 year you now have 200 trout. Now it does say here, the trout will be limited by the availability of resources. A small population might start exploding exponentially if the pond is very large and food is abundant, but eventually the growth rate should decline. And a nice model for this is the so-called Logistic Model. So you may have seen this when you've been reading about populations, maybe you haven't, but these questions are self-contained. All the information you need to do them is in the model. So we're not really going to, look at the information at the top now. What they first want us to do is explain why does this model called 1, why is this why can this be approximated by the exponential model for very small populations? And then we actually want to use this exponential model to make some predictions. So if you look at the model called 2 versus the model called 1, the real difference is that coefficient in the middle of 1. So that's kind of vanished. That's just turned into a 1, so it seems. And I think that's the key observation here, is that when p is close to 0, then, well, the term 1 minus p over n, so as long as p is much, much smaller than this parameter n, this is going to be approximately 1. So for small p's, this will be approximately 1. So hence the small p values, small populations, we could try to model growth using, well, we're told that this is the model we want to use. We're told it's this model here. And it's saying that, well, if p is very, very small, I'm not going to really be able to see the difference between this term and 1. So approximately, this looks like the model k times p. Now another way you could do this is you could also expand this and see it's a p minus a p squared, and a p squared term is much, much smaller than a p term when p is close to 0. So that is a model we could use, and this is the model they call 2. So actually I might, so this is the exponential growth model. So that wasn't the only thing we were asked to do. We also asked to then use this model and predict what it would say the population of trout would be after 10 years. Alright. Oh wait. You estimate the population after 10 years and discuss the behavior as p tends to infinity. So this is the exponential model. Now it is a first order linear equation, so you can solve it using the methods of first order linear equations. Maybe you already spot this and know that this is a you already know that this what the solution is, but just in case you don't, I might try and solve this. And in fact, this is two types of equations we've studied. This is both first order linear and it is separable. So I really am spoilt for choice on how I want to solve this. I might do it as a separable equation. So I will do it using separation of variables because I can write it as dp over p is k times dt, which integrates to well, we're just trying to integrate the following, which gives us, well, it gives us the log of p is equal to k times t plus a constant. Now I don't really want to know about the log of p, I would like to know about p, and I can solve this equation to give me something for p. Solving for p gives, well, we're going to get the exponential of the log of p is equal to the exponential of kt plus c, and we should recognize this from before. This is what Adele had when she was looking at that data measured in a laboratory. So we have that p is equal to e to the kt e to the c, and e to the c is just a constant, so I'm going to write this as a e to the kt. So there are many different paths you could walk to get to this, but this is the solution. It is just an exponential growth, kind of indicated by the name of the model. Now we do have two parameters here we need to fit. We need to fit this a and we need to fit this kt. So we really need to look at the original question and pull out the two pieces of information we need. One of them is given quite explicitly, the other one slightly hidden in the text. Not very much, but it's not just a straightforward number your eyes can see. So if we're looking at the text, we said we have that, well, we have the initial conditions. We have that the population initially is 100, and we were told that after 1 year, remembering t is measured in years, we had double the population, which means 200. So from this we get that, well, actually maybe I should write it here. This is a e to the naught, which is just a, and this is a e to the k. So this is nice because the first one actually just tells me a immediately. We get that a is just 100. This one doesn't quite tell me what it is, but it's very easy to find it because we get that 200 is equal to 100 e to the k. So just looking at this one here, e to the k is equal to 2, which implies k is log 2. So we have the parameters we need in our model. We know the a and the k. Now we can use this to estimate the population after 10 years. So when t equals 10, what does this predict? This model predicts, well, it predicts that the population is going to be 100 e to the 10 log 2, which is really the same as 100 2 to the power times 2 to the power of 10. And you can use a calculator, but this 2 to the power of 10 is at 1024, so it's predicting this number here. It's predicting over 100,000 trout, which is quite a large number. And we can see actually this model's not very realistic, because if we take it and look at what happens for large values of t, it just keeps growing. So we can also see that, well, p of t, which is just, well, 100 times 2 to the t, tends to infinity as t tends to infinity. So this model population, whoops, grows without bound. That really means I'm not going to really trust this model for very large time values. Maybe initially it looks like a good model, but it doesn't really stay realistic forever. So that's an interesting model to look at, but now they want us to return and look at the logistic model. And they want us to try and notice that this model is more realistic than the exponential one. We know for small values of p they're very similar behavior, but for large values, as p gets larger, they behave quite differently. So this first part is actually, I think, it's quite hard. It asks you to explain why this parameter in the model called n is called the carrying capacity. And you really have to think about what happens when p is close to n to get what's going on. So what you might notice is that if, for example, p is less than n, then what that means is p over n is less than 1. And that's quite important, because there is a comparison here between 1 and p over n. So what I'm seeing here is that 1 minus p over n is actually a positive quantity. So that is. So that means if I'm at a population level below this parameter n, the so-called carrying capacity, this term will be positive. So what I see is that the rate of change, dp dt, which is k 1 minus p over n times p, well, population is positive. Now actually, I do think this question should have been a bit more explicit. K is also positive, as is n. It says real constant in the question. I think they should have said real positive constants, because when you try and fit it, that's what you get. So this term is actually positive, and this term is also positive. So we get that the population increases. So hence this is greater than 0, and so the population increases if p is less than n. And you can also see interesting things happen when p is equal to n. So when the population, if the population was equal to that n value. Similarly, if p is equal to n, well, then you see that p over n is equal to 1, and so dt, the rate of change, which is just 1 minus p over n, that's just going to be 0. So that tells me that this is actually a stable population number, that if I was at this population level, the population would not change. The population doesn't change. If p is equal to n. And one more comparison, let's just look at what happens when our population exceeds the carrying capacity. So finally, if p is greater than n, so we've exceeded this so-called carrying capacity, then p over n is now greater than 1. That is, well, we have that 1 minus p over n is negative. So this combination here is going to be a negative number. So here the rate of change is, well, it is just, well, it's going to be this constant and this constant times this negative number. So k is actually positive. So we're going to get the rate of change of population is decreasing with time. That means the population is dropping. We've exceeded how much population we can really hold. So meaning the population will drop if p exceeds if p exceeds n. Let's write that a little bit nicer.
Can I suggest here it's maybe easier to visualize this if you actually draw the curve.
Mm-hmm.
So if you draw a plot and you've got dp dt, which is equal to k into 1 minus p over n times p, versus p, it's actually a quadratic, which I haven't drawn very well, but this here is n and this is 0. Okay? And so I might draw it again because it really should be a symmetric curve. Not much better. But anyway, you can see that this curve is all of this term here, right? And so you can see that it's negative here, and it's positive here. Now, for a negative population, that's not meaningful, right? So you've got maths, which actually is happy for p to be negative, and you've got reality, which says, well, a negative number of trout, well, that's crazy. So p has to be non-negative. But here it says p to t is positive when you're in here. That means that the population is growing in this area here when p is between 0 and n. Right at p equals n, There's no change, nothing changes. And so it's going to head towards n. If it hits n, it stays there. If it gets too big and it's bigger than n, then you're in this region here. P to t is negative, and so you're going to be dragged down in p, right? Because P to t, with time, p is going to decrease when P to t is negative. So sometimes it's really useful to actually draw a plot of the right-hand side of your differential equation, and that gives you how you're changing in time.
Yeah, so I really do like that part. So yes, it is much easier to see what's going on. So we can see p is increasing, so we will have this increase. Everything inside here will move towards n. So yeah, that's very nice. And also, I guess if you were stuck for how you would make progress in this, the plot is a very nice starting point to get you to see what the behavior is for different p's. Now we're also given a solution, and we want to talk about what happens to this solution as t tends to infinity. So first part is verify what we've given you is actually a solution. And that really just means make sure what we've given you does satisfy the differential equation. And the easiest way I think to do this, well, is just to substitute into the left and right hand side, make sure they both do the same thing. So, taking the proposed solution and substituting into the left, hand side of what they call equation 1 here gives, well, it's just a derivative. So we're going to have to take the derivative, so it's going to be the derivative of what they proposed. It's n over 9e to the minus kt plus 1. So, well, this one's not too hard. It's really just going to be the chain rule. So you know how to take derivatives of 1 over something. I mean, it is a quotient, but the top is a constant, so that's not going to really affect us. So it's going to be, well, derivative of 1 over something is minus 1 over that thing squared. We get a minus n over this squared. And then we need to multiply it by the derivative of that term on the bottom. You can get this using the quotient rule. This is a quotient, but one term is a constant, so you'll only have one term in the entire rule. So this is just minus n, well, this derivative is not too hard to do. It is minus 9k e to the minus kt. And it's going to be over this term squared. Now I want to start on the other side and see if they meet in the middle, see if they join perfectly like they should. So let's take that proposed solution and plug it into the right hand side. So substituting into the right hand side, gives, well, we're going to have k times 1 minus p over n times p. So k is just k, doesn't do anything. this is going to be, well, I'm taking this term and dividing by n, so it's 1 minus 1 over 9e to the k t plus 1. So the n's really just cancel out in that, and I get the thing again. So n times 9e to the kt plus 1. Now as it stands, I don't quite see it, but they're not too dissimilar. I should simplify this here. So put these two over a common denominator and combine. So this will give me, so putting it over a common denominator of 9e to the kt plus 1, I get 9e to the kt plus 1 minus 1.
9e to the minus k.
Ah, yes. Oh, thank you. Hopefully I would have spotted that before finishing.
And in the numerator as well.
Yes. And that was over 9e to the minus kt plus 1, all times what was on the outside. So, well, this is just plus 1 minus 1, that term goes away. These two terms combine to give me a square on the bottom, and I really do just get k n, well, 9kn e to the minus kt over 9e to the minus kt plus 1 squared. And well, I really should have cleaned this one up a little bit more, because now I see there are two minus signs, and that's kind of an ugly way to write that. I really should have written this as 9nk. So just cancel out the minus signs. And you really do have the same terms here. I've swapped the order of k and n, but scalar multiplication is constant, so that's fine. So this is as required. So in an effort to maybe be very explicit with my conclusions, so this is a solution of the equation they called 1. And I would like to know what happens, what does this model really do for large values of t? So I'm really wanting to understand what is the behavior of this exponential of large values of t. Any comments before?
No.
No. So just to note, as t tends to infinity, well, what's really of interest is this term e to the minus kt. And k here is a positive constant. Oh, it should be. This should tend to 0. So, done it. We have e to the minus kt tends to 0, and hence, well, I'm going to find that the limit, as t tends to infinity, of this population, which is n over 9e to the minus kt plus 1, that's really just going to n over 0 plus 1. It's going to n. Which makes sense, because we know that we should be heading towards the carrying capacity as t is increasing. So
if you're above, remember, because of the logistic equation, if you're above n and you start above n, you will decrease down towards n. If you're below n, you'll increase up towards n as time continues. So as you go off to infinity, all paths lead to n, whether you are above or below. And that's why that's called the carrying capacity. It's the state that can exist as a steady level of population given that particular environment.
I might state the conclusion clearly, as Adelle said. So hence, the population, well, it tends to the carrying capacity. Now they would like us to use this model. So they're saying, let's assume that the carrying capacity is 1,000. So this number n here is 1,000. Find out what the population would be after 10 years. And then compare your estimate to your results from part A. Now, there is actually, I think, it could be a bit of a choice here about how you're going to use k. Because we found a k value earlier for the exponential growth model, and for small values of the population, the two models are very similar. I don't think 100 is really small enough for me to feel comfortable using that value, so I'm going to find the new constant for this logistic model. So, well, we have two parameters. We have the carrying capacity, which we're given, and we have this k. So we need to really fit that k again. So, let's see. We're given n is 1,000, and our conditions, our two conditions, say you should have that p at 0, which in this case is n over 9 plus 1, which given that n is 1,000 is 1,000 over 10, it is 100 as required. So they've already really given us this one. This is not something we need to work on. But we're also told what happens after 1 year. We're told that, well, it'll be the carrying capacity, which in this case is 1,000, over 9e to the minus k plus 1 is equal to, well, it should be 200. So this is an equation. It's not too difficult an equation to solve for k, so let's just solve it. So firstly, I might bring the other term on top, so I'm going to flip this over to, we have 9e to the minus kt plus 1 over 1,000 is equal to 200.
T is 1.
Ah, yes, thank you. So that gives us that 9e to the minus kt, minus k, sorry, plus 1. Well, I need to, I made a mistake, 1 over 200. So yes, I flipped both sides over. So I'm going to multiply this by 1,000. 1,000 divided by 200 is 10 on 2, it's 5? Yep. Yeah, 500, 5 200s. So we're going to get that 9e to the minus k is equal to 4. Or in other words, e to the minus k is equal to 4 ninths. So that's very close to giving us k, because we can take logs to get minus k is the log of 4 ninths. So k is equal to minus the log of 4 ninths. And I might just point out, a minus sign in front of a log can flip it over, so this is really the log of 9/4. So 9/4 being 2.25. So it's close to the log of 2, which is what we used before.
Yeah, and either way, k is positive, because
yes,
if you think of a number between 0 and 1, the log is negative. And so a negative of a negative is a positive. 9 on 4 is bigger than 1. Log of 9 on 4 is, again, positive. So either way, that k is positive and it's very close to the previous k, but not the same.
How would you feel if a student did use the previous k?
I think that if the student did use the previous k, they're not using the same model. And so the problem is that it's going to be an approximation for a value. And so as you can see, the n equals 1,000 actually meets at the initial point only. But if you have the wrong k, then actually it's a different model. And so it won't meet the criteria that actually meets that condition after 1 year. So the model will be wrong in 1 year and thus be wrong for any other year as well. So it'll only be correct at t equals 0. So I think that the strategy is, again, always extract the information from the question and make sure that you then start again and say, okay, if this is my model, this is the way I'm going to use that extracted information. And then in part 2, part B for this, you're actually saying, okay, there's my extracted information, here's the next model. And make sure that each model is self-consistent. Otherwise, it's not actually meeting those initial conditions, and that condition at t equals 1.
So we need to use this information to make a prediction at t equals 10. We want to see what our model's doing after 10 years of running. So we now have the parameters we need, we just need to plug it in. So the logistic model predicts, well, the population at 10 years is just going to be 1,000 divided by 9e minus 10 log of 9 over 4 plus 1, and you really just do need a calculator for this. Well, I did actually calculate this before, so maybe I'll look at my solution.
Please do.
Here it is. So yes, this is just something you can plug into a calculator, and I think that's all you would do for this point. Yep, here. So now I didn't write down the full thing, and in fact I wrote it to the nearest integer, because when I did it, it came out as 997.3. So the nearest integer.
Well, the integer below, you can't have a half a fish.
Yes.
So.
But I'm not rounding up.
Yes. So you must round down in this instance, because a fraction of a fish is no fish at all. So.
Yes, I mean you might want to round up, saying that if there's part of a fish, it must be a whole fish. You might want to say, well, a fraction of a fish is not a fish, so I'm rounding down. I'm just going to go to the closest integer. If I had 997.9, I think I would round that up to 998. So just do what I'm saying. I'm just doing what I'm saying here. The nearest integer to my answer is this. I don't want fractional fish. Right, so that's that part. And the last part is, so you can see this is already quite high. It's quite close to the carrying capacity. It's only 3 fish off, in fact. But it's much more conservative than the exponential model. The exponential model at 10 years gave us over 100,000 fish. This is a bit more realistic. Now what we'd like to know is, how long does it actually take us to get to 90%? Well, we're already at 99.7% here, so less than 10 years. I can say that much. Let's say more though. Yep. I'll keep that k value. So our model will be at 90% of of the carrying capacity. When? Well, it's going to be when P of t, which is 1000 over e to the minus, well, I'll use my k value, which is log 9/4 t, plus 1 is 90% of the 1000, which is 900. So the t value, which gives me this. And this is not too bad an equation. I might do it slightly differently than I did before. I might just bring this term up here, so multiply through. So we know that this tells us that 1000 should be equal to 900 times this. And yeah, we can isolate the exponential by itself and finally take a log. So this is just a little bit of algebra. It's not really too much to it, but let's just do it. We get that, well, I should really divide by that 900 to give me 10 over 9 is going to be e to the minus log 9/4 t. No, wrong. Plus 1. I need to subtract 1 from both sides, so that's going to be 10 over 9 minus 9 over 9 is 1 over 9.
Negative t.
Negative t? Oh, my t's vanished. Yeah. E to the minus log 9/4 t. Now I just need to take a log to get rid of this exponential, so I'll get a log on this side. So we have that the log of 1/9, which is a negative number, is going to be minus the log of 9/4 t. So this tells me that t is going to be well, it's going to be the log of 1/9. Minus the log of 1/9 over the log of 9/4. And that's good because this top number is minus a negative number, so it will be positive. So we didn't start close to 90%, so it has to be in the future. So that makes sense. And approximately, if I do put this, into there. Oh, I dropped a 9 somewhere. So it seems I've dropped a 9 here. So there was a 9 in my equation. So that 9 becomes 9 here. So it's actually 1 over 81.
Mm-hmm.
Now,
Still a negative number when you take the look.
Yes. I guess I would be curious to know if I would have spotted my error, because when I look at this number here, I get to 3 significant figures, 5.42. I'm just going to say this is 3 significant figures. You can leave your answer like this, but for these sort of numbers, I like to see what it says to see whether I think my answer is sensible. So if I...
And you really need to answer in words.
Yes.
Because T is an invention. It's a label for time. And what's time measured in this case?
Years.
So this is actually about 5.5 years. How does that match with our long-term time? Well, we saw that we were at 97 or 99% of carrying capacity at 10 years. This is before that, so we would expect that we would reach 90% of the capacity before we'd reach 99% of the carrying capacity. So things are matching. So we just need to sum up here to say that it's about 5.4 years to reach 90% of the carrying capacity.
Yes. So actually I will add that as a conclusion of, so write it out in words. So we reached 9% of the carrying capacity at about, well, I'll just say it's 5.42, 5.5 years. So 5.4, around about 5.5 years, years, plural. I think there's another question.
Indeed there is.
So this one says to, well, just give a sketch of what both the exponential model and the logistic model look like, and do it on the same set of axes. So we want to really compare these two models. So I might remind you what the solution we had for the exponential growth model was. I guess I'll rub this all out. By this stage, we've already worked out a number of different points in time. So we can use that information to make our plot look better. So I'm going to try and do a plot, sketch over 10 years. And to make it interesting, I might put the carrying capacity at about halfway up. So this would be the 1,000th. Now we know we do start at 1/10 of that, and we're going to have 10 years, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And well, the scale I'm giving, the exponential growth is already going to be well off this plot by the end. But I'll just remember that we had that the exponential growth gave, well, it actually gave us that the population was 100 times 2 to the t. So that's actually quite easy to plot because it starts at 100. After a year, it's up at 200, then it's doubled again to 400. Then it's doubled again to 800. Then after another year, it's gone to 1,600. So we're already beyond the carrying capacity. And the next point is actually off the graph. It's at 2,000 or 3,000 something. So it's gone all the way up there. So this is our plot of what exponential growth looks like. So this is P of, well, yes, it's P of t equal to 100 times 2 to the t. So it doesn't take long before we've exceeded the carrying capacity. Now what we realized is that after about 5.5 years, so 1 year, 2 years, 3 years, 4, 5, 6, 7, 8, 9, 10, with about 5.5 years, we were already at 900. So we already had this point here. We're already very close to the carrying capacity. And at 10 years, well, we were only a few fish short. We were really high up here. But for small values of t, it actually does behave pretty much like an exponential model, so we get very similar behavior for small t. So it initially does behave very similar. But then as we get closer, and this is actually where Adelle's earlier plot is quite helpful, something I didn't mention before, is if you remember Adelle's plot showing dp dt versus p, this is the rate of change with time versus population, well, very close to n, you get that the rate of change is actually getting smaller. It's slowing down as you're approaching n. So that's really what this is saying here, that dp dt is small when p is approximately close to n. So that's what I'm sort of seeing in this baby here.
The other really, it's a nicety, but you can see that the peak actually, because this is a quadratic, it occurs exactly halfway between the two zeros. So at n on 2, you have the highest change. So the slope of this curve is going to be the highest at 500. So if you go across here, this is where it's going up the sharpest. So logistic curves have this nice thing where they increase in their rate and then they curl off again until they become pretty much flat. Right at the carrying capacity, it will be at 0. So just here, it's going up the fastest.
Yeah, thank you, that's a very good observation. I didn't notice that before. So yeah, this is the biggest slope here in the middle. Oh, that's good. Okay, and I think it's one last question. We're given another model. This is part D. And it looks very different from the other two, but actually you might find it's very similar if you were to dig really deep into it. But it says here that without solving this, we don't want to solve this equation, because frankly I don't think I could, not without a bit of time, and even then I'm not sure. But we can see what the behavior is for different values of p. And maybe this is where a plot would be helpful. So I didn't think about this when I was preparing, but actually I'll give it a go, see what it looks like. I might try and plot what this looks like for different values of p. So we can see actually again that when p is close to n, p over n is close to 1, and log of 1 is 0. So it is going to be 0 at p equals n. Let's see how this goes. So I want to look at dp dt on this hand, on this axis. And I'm looking at p on this, and I know something special is happening when p equals n. So when p is greater than n, well, the log of a number greater than 1 is positive, so it will be negative there. Yeah, I think I might have a hard time plotting this one.
It's going to be really rapid,
Yeah.
and then it's going to curve over. It doesn't exist at p equals 0.
But the limit does tend to 0 as p tends to 0.
Log of p, yeah. Log.
So p tends to 0, but
log wins.
no, log can't it? No, I don't think log can beat a polynomial. Well,
No, you're right.
yeah, maybe I won't try to do the plot, because I think I'm going to have a hard time plotting this.
Start talking and I won't.
Yeah. So I think I'll stick to the algebra for now. But what you can notice is that these two models look very similar. They've just replaced that term, that 1 minus p over n, with this minus log. So for part D, well, you can see that the difference, the change between these two models is that well, you've really replaced this term, 1 minus p over n, has been replaced by minus the log of p over n. Now what's important is I want to think about what these two different things are doing as p is close to 0. So what happens as p tends to 0? So as p tends to 0, well, this term is actually fairly nice. So as p tends to 0, you have that this term, it just tends to 1. see. But, well, as p tends to 0, we also notice that minus k log n, p over n. Well, the k is not changing anything. What's really happening is p is going to 0, and the log of a number tending to 0 is going to go to negative infinity. But this minus sign here means that this is tending to minus infinity, and this sort of corrects that and makes it positive infinity. So this term here is tending to infinity. So that's really telling you that the difference here is this term is actually, this term here does have a larger value as p is tending to 0. So what I can see is that minus, oh actually, what am I saying? Oh, there's no k there. So this term does tend to minus infinity. So hence you're going to find that k 1 minus p over n times p is going to be less than minus k the log of p over n times p as p tends to 0, as we're looking at numbers which are close to 0. So the growth of this one will be greater than that one.
Yeah, so it's skewed to the right, left. So it's basically very rapid, going up, and it's got a longer tail. I've perhaps drawn it badly. So wrong. It's more like that for the log one.
Yeah, I was thinking about trying to look at the slope, but actually I think the slope is also, it turns out to be an undefined quantity. It turns out to be.
It's better actually to compare, if you're thinking about these, the terms that we've got. So 1 minus p on n compared to minus log p on n.
Yeah, so here.
Yeah.
I think
so
looking at this
again, I'm a graph type person, so I would be plotting this thing, right? Which, if you think about it, a log function looks like this. So minus log is going to look like that. Right, so this is minus log of our p on n. And then you want to compare with 1 minus p on n. Okay, so this here, okay, is going to occur when p is n. This is going to be, when p is n, this is going to be 1, it's going to be up here, and it's going to, when p is 0, it's going through 1, so it's going to look like this. Okay. So these factors... Slope, I think. Oh, sorry. You are absolutely right. So coming down.
But they both hit this point, right?
Yes, you're right. I should always practice these things before I talk. Okay, so... Right, yes. You can see here, if this is n, and I really should have scaled it up, this point here is our point of comparison. We've got a nice quadratic, which is symmetrical, and our log function is pushing it so it's faster rising at the front and slower at the end. So it's basically a nice model actually for cancer growth. It's called the Gompertz model. And so it means that when you've got a rapid rise at the start and it then tails off, so it makes it non-symmetric. So that point where it's the highest growth rate is actually moved to the left a little.
So I might just finish with the conclusion and then we'll stop. So model 3, well, however you do explain it, I think this graph is very nice, but yeah, it does need to be, you really need a detail here. So model 3 does grow faster. And actually it grows much faster than model 1 for small. P. Okay. So I think that was the last question from the 2018 exam.
I might just put up the end of the examination,
Yes.
but also perhaps we should just go back to the
Writing tips?
the writing
Yeah,
guide. So I'll just move that up. So
I should have worn my glasses.
okay,
wait.
I'll come and do that because I have the right ones on. Okay, so remember, it's not just about doing it, it's about actually making sure that you can write your work clearly in sentences, okay? And I'm sure we've got it on a piece of paper here. The idea is that you need to be able to have sufficient detail available on the page so that your examiner can see what you're doing and what information you're using. Make sure that you actually put everything that you need down and define what you're doing. Okay? So, any other tips?
Yeah, I suppose I still think the simplest way I've heard to write mathematics is to say what you're going to do and then you do it.
Yes.
It's a very lovely pattern to follow. You
Yeah,
say,
and
"I'm going to do
concise.
this, and here it is."
Yes, and concise and to the point. One particular thing is make sure you write mathematical sentences correctly, just like you write English sentences. Don't just write random things that are mathematical symbols down the page, but make it a mathematical sentence. This left-hand side expression equals this right-hand side expression. Therefore, doing this manipulation means that the left-hand side is equal to the right-hand side. So make sure that you always have a left-hand side and a right-hand side in any field of view. Don't start a new page with no left-hand side. Otherwise, it's like walking through the door and not greeting someone and just starting halfway through a sentence. It's really important to make sure that you are concise, but also very precise, and don't put unnecessary information which may actually dilute your message.
Okay, so thanks for joining us and we wish you the best of luck with the exam.
Yes, and all the best for your future studies.